recording right now. So, so we got 2 more days where we're working with these linear systems. And so, so the last time we talked about taking a triangular system, and that could have either been an upper triangular system, right, an upper triangular matrix, which was in the form ux is equal to b, could be a lower triangular matrix, which we didn't deal with, but Lx is equal to b, and then also a diagonal matrix that would give us this system where dx is equal to b. These were our 3 different conditions or situations of triangular matrices or diagonal matrices that, that would allow us easy solutions to our system, because ultimately we want to solve for these unknowns, x's, right? And so, and this whole theme that we've been getting at is that when we have a system that's ax equal to b, we want to avoid doing this, okay? We want to avoid having to take the matrix inverse. And so we concluded last time that anytime that we have an upper triangular matrix, that you can use an algorithm that's called backward substitution, you know, which I think was intuitive to work out by hand. As we shifted that into a numerical algorithm, you know, that's something that really just takes a lot of practice and time doing, so that you can do that more quickly. But hopefully by the end of the class period, and then after you worked on your homework on the practice problems, that you're comfortable now, you know, taking this backward substitution idea into numerics. Okay, so that was the whole goal of just getting used to this process. Now, today, we want to take a look at how in the world would when can we then use this to actually solve a system that's ax equals to b. I mean, you know, it's nice, great. We get an upper triangular matrix and an upper triangular system, but when do those things actually occur? Or today we're going to talk about how can we force that scenario so that we can use the backward substitution algorithm. Okay, so excuse me. So today we're not going to do anything with MATLAB. Sorry, we're not going to do anything with MATLAB. It's all going to be handwork, because I want to make sure that you understand the process. And then for your practice problems, there's an algorithm in the book that's already given to you, and I want you to first understand it, and then to improve that, you know, using some of the what I'm just going to call best practices in coding. Certainly better practices than what the book actually shows you. And I think by going through that process, you're going to get a good handle on the algorithm itself, which is called forward elimination, and then from that be able to solve those problems. Okay, and it'll set us up for one tweak on that we're going to make tomorrow. Okay, so this is kind of our first step into forward elimination, and then tomorrow we'll take it one more step. So, so to set this up, I want to look at the same 2x2 system that we did in just a couple classes ago. And so this is when we were talking about Kramer's rule. We had the system 3x1 plus 2x2 is equal to 18, and then negative x1 plus 2x2 is equal to 2. All right, so what we did here is that we said we want to eliminate variables. So that's the process that we went through. We said that to do that, and to do this systematically, I want to eliminate x1, x sub 1. So I'm going to take the coefficient from equation 2. Today I'm going to number our equations as we walk through. I'm going to take the coefficient from equation 2, which is negative 1. I'm going to multiply it by the entire equation 1. And then for the second row, I'm going to multiply it by 3. So remember, we took those coefficients and then we subtracted them. Okay, and then after we subtracted it, we got 0 for our x1 because we had eliminated that variable. And then we get negative 8x2 is equal to negative 24. Okay, so what we have here is a equation 3. And so equation 3 um, is a combination of equation 1 and equation 2. Okay, and that is a key factor here, is that um, by approaching our problem this way, you know, equation 1, when we multiply it by this coefficient, because we're doing the same thing to the left side that we do to the right side, equation 1 doesn't change. And equation 2, because we're multiplying both sides by the same number, positive 3, equation 2 doesn't change. And so equation 3, we say that, you know, equation 3 is going to be a function of, or a, let's do it this way. It's equation 1 minus equation 2, right? Because equation 1 and equation 2 haven't changed. And so this is a combination of the two. All right. So, and because this was a 2 by 2, we just solved for x2. And, you know, and then once we had x2, we just plug that into, you can either plug it into equation 1 or equation 2. All right. So the whole idea for why we can do this is it's based on these two things. You know, first what I said is that when we multiply by a coefficient, we're not changing the equation. And this new equation, because it depends on these two, we say it's a linear combination of the two equations. Okay. And so, so would it be legitimate to say, so this is a question to think about, would it be legitimate to say that we're solving this system using 3 equations? Because is that a correct statement or an incorrect statement? Anybody? I don't know how to do polling on this.
Wouldn't you be able to modify equation 3 and then use whatever that's equal to and substitute into the other ones to figure out what the unknowns are? Is that what you're looking for?
So that's what we did, right? We took equation 3, we solved for x2 and just plugged it in. Okay. And so, but I guess my question is, do we have 2 equations here or do we have 3 equations?
Got it. Sorry about that.
Yeah, that's fine. That's fine. Let me give you a hint. Look right here. If we have equation 3 and it's a combination of equation 1 and equation 2, that means that equation 3 just isn't that unique. Okay, because it's made up of these 2 other equations, right? So even though, you know, we're even numbering them 1, 2, and 3, we started out this system with 2 equations, right? And by making this new equation, right, or a new formula, it's nothing that's unique. And so what that allows us to do is we can just say we can say this: there are different ways to combine equation 1 and equation 2 to make an equation 3. And so here's what I mean. So, or different ways to combine, let's say, these 3 equations. Okay. And so let's want to make that statement, and I want to show you what I mean. So we can combine equation 1 and equation 2. And if we do that, then we get, I'm just going to write it out. So 3x1 plus 2x2 is equal to 2. And then, so that's 1. And then with equation 2, right, is negative x1 plus 2x2 is equal to 2. Right, those are my 2 that I can combine. I can combine equation 2 and equation 3. And so to do those 2, it's 3x1 plus 2x2 is equal to 18. Oh, I think I messed something up here. Let's correct this. That should be an 18. Let's do x2. Okay, yep, is 18. And then I can, if that's equation 1, and I combine it with equation 3 tells me it's just negative 8x2 is equal to 24. Okay. And then I can also combine equation 2. Well, I'm getting these mixed up, excuse me. This is equation 1 and 3. Let me make sure I'm doing this right. And then I can combine equation 2 and equation 3. And if I do that, this is negative x1 plus 2x2 is equal to 2. And then equation 3 is equal to negative 8x2 is equal to 24. Okay. And so, let's take a look at this. All right. So if we've got equation 1 and equation 2, which we've already solved before, okay, we can get the answer x1 and x2 out of it. And if we were going to put this in ax is equal to b form, so this form would look this way, where we get a 3 and a 2, a negative 1 and a 2. x1, x2 is equal to 18 and 2. And so we've already solved that system before using Cramer's rule. And we've already solved that system before using the elimination of variables. Okay, if we were going to put this next form into the same, the next system into the same form, then we're going to get the coefficients 3, 2, 0, and negative 8. So here, 3, 2, 0, negative 8. And then my coefficients are 18 and 24 for my B matrix. Okay. Is everybody following me? We have thumbs up here. Okay, I'm just taking these equations and I'm shoving them into this AX equals the B form.
Should it be minus 24 or is it 24?
Oh, you're right. Thank you for that. So both these minus 24. I appreciate it. Okay. And then let's take this next combination of 2 and 3. And then we would get, for our A matrix, negative 1, 2, 0, and negative 8. And then for the B matrix, 2 and minus 24. 2 and negative 24. Okay. Now, the purpose of showing you this, okay, is that first I want to show you that this equation 3 is just not unique. Okay, so what you can do is you can take equation 3 and you can replace either 1 or equation 2. All right, and then that set of equations, equation 1 and equation 3, becomes its own system. And then if you solve for these, you're going to get the same answer, whether we solve this first system, which is equation 1 and 2, the second system for x1, x2, which is equation 1 and 3, or this last system, which is equation 2 and 3 for x1 and x2. We're going to get the same answer each time. Okay, and all we've done is we've just, plug this in or replace that equation. All right. Now, I don't need you to like understand all the ins and outs of that. I kind of need you to just accept it. Okay. There's lots of things in linear algebra that you can do to determine whether a system is linearly independent and that kind of stuff. But that's not the purpose of our class. Okay. But the purpose of the class here is to then let's look at the form that when I make that substitution, right? Now I've got equation 1 and 3 together. What form is this matrix? It's an upper triangular matrix. Okay. And so we get here, this is actually U times X is equal to, and it's not B anymore, it's actually a B prime. Okay, because we've changed our coefficients, like our AX is equal to B is this form. But we've now changed our A matrix to be this form simply by solving, by eliminating a variable actually. And then we get a new B matrix. Okay, can everyone see that? How we went from an AX is equal to B to a UX is equal to some new B matrix. Give me a thumbs up if you're following me there. Okay, it's kind of a weird concept. Okay, it's one that you know, as you work with linear systems more and more, you need to remember that that's the case. Okay, so that way you're not duplicating solutions. But the point is that we can turn just about any system that's a square matrix, AX is equal to B, into a system that's UX is equal to B. And as soon as we get UX is equal to B, then we're able to use backward substitution to be able to solve for X. Okay, so that's where we're headed. And I think that a good way to do this is to let's go ahead and go into a 3x3, and let's solve this by hand. And so we're given this system, AX is equal to B, and we want to transform this into a UX is equal to a B prime. And we want to do it using the forward elimination. Okay, so our system that we have is -3, 2, 1, 6, -6, 7, 3, -4, 4. It's multiplied by x1, x2, and x3. And our B matrix is -1, -7, 6. Okay. So if you see this, I mean, of course, we can use Kramer's rule to work this out. It's a 3x3, so it's containable. But as we're working through this, I want you to think about how we would expand this to a much larger matrix and much larger system. It's a 3x3 here. Maybe it's a 6x6, or it's a 14x14. How would we go about doing this, right? So now, because we're doing the same thing to both sides of the equation, okay? So every time, you know, we're going to work through this process, okay, of applying coefficients to the left-hand side and the right-hand side of each of these equations. We're gonna create a new matrix, which we're gonna call it A tilde or A curly hat, and this is an augmented matrix. And if you remember what augmenting is, it's where we're putting one matrix next to the other and forming a new matrix. So it's a container, right? Every matrix is simply a container. And so this is a matrix of matrices. And so this matrix A curly hat is going to contain both the A matrix and then the B matrix. So let's put those in. So let's put in our A matrix first. So to describe more clearly what we're doing, we're putting them together. And so we're putting together a 3x3 and then a 3x1. So it's going to give us a 3x4, where we get -3, 2, 1, 6, -6, 7, 3, -4, and 4. And then the vertical line that's separating the two just indicates that this is a combination of the two matrices. And then we're going to put in our -1, -7, and 6. And so now this is our augmented matrix. Okay. And our goal here is to make it to where we're going to transform this system, because we're going to do, like I said, the same thing to both sides. So we just put them all in one matrix for convenience. Okay, instead of taking two matrices with us, we put them all there, and we're going to focus on working out the zeros. Okay, we want a 0 in this 2, 1 spot, a 0 in the 3, 1 spot, and a 0 in the 3, 2 spot, to give us an upper triangular matrix or an upper triangular system that then we can solve using the method that we did last time. Okay, so that's where we're headed to. Okay, we're wanting to I want zeros in those spots. Okay, so let's do that. How we're going to do this is we're going to work with the first column first. Okay, so we're gonna work to get a 0 here and then a 0 there. So in the first column. So let's get zeros in the first column. And to do this, we don't have any reason to work with the first row, or at least to try to get 0 in the first row, right? Because we want numbers on the diagonal, right? So we're not trying to eliminate anything in the first row. We're going to start with the second row and then move to the third. So to do that, let's pull out the first row, because that's going to be our tool that we use to eliminate those variables. Okay, we're not doing anything but variable elimination. But I do want to pull out the first row. And that first row is -3, 2, -1, and -1. Right, so it's a 1 by 4 that we're taking out. And then I want to write down the second row, right, which is 6, -6, 7, and -7. Okay, so those are our two rows that we're working with. We want to get rid of the 6. And so to get rid of the 6, let's set this up where we are multiplying. Remember how we did this before? We're taking that coefficient, we're multiplying the entire row by that coefficient. And then last time we talked about it as multiplying this entire row by the -3. Right, so -3 and a 6 is what we did before. And the reason for doing that was really deliberate, to be able to show Cramer's rule, because that's the form that Cramer's rule is taking. In this case, I want to set this up a little bit differently. Instead of multiplying 2 rows by something, I want to set this up as a 6 divided by -3. Okay, so we're still getting our coefficient, coming from there. We're getting your coefficient coming from here, to give us the factor 6 divided by -3 that we're multiplying through. And then the next thing we're going to do is we're just going to stick a negative sign. So this is the algorithmic approach, okay, where we're taking the coefficient from the term we want to eliminate, multiplying it times the row that we're using. Okay, then the coefficient from the term that we're using, right, to eliminate that next row, and then putting a negative sign in front of it, and we just add them together. And then we get a new matrix, which is 0, -2, 5, and -9. So we've eliminated the 6 by multiplying through by a -2. I'm sorry, +2. Right, so then, I got that right? I think so. Right, so we get a 6. Yes, that's right. So +2, so -6 plus 6 is equal to 0. Okay. Now remember that we said earlier, so if this is my first equation, that's my second equation, and now I've got a third equation. That with this third equation, it's a combination of the first two. So I can just take this third equation and substitute it either for that row or for that row. Okay, so do you remember where we talked about this here? I can just toss this third equation wherever I want, so I can just replace it. So that's exactly what we're going to do. And so we get from this a new equation, or a new matrix, our A tilde. I want to keep that first row, so -3, 2, and 1, -1. And then I want to substitute in this equation, this third row, for the second row. So let's do that. So this becomes 0, -2, 5, -9. And then we haven't done anything at all to the third row. Um, Get this back up there. 3, -4, 4, 6. All right, so then we haven't done anything at all for our third row, so we just keep it the same. So which is 3, -4, 4, and 6. Okay, so what we've done in that single step is that we've put a 0 where we want the 0. And so then we're going to do the, finish out this first column. And then we're going to operate now on the third row and put a 0 here. And so to do that, we're going to take our first row. And so our first row is -3, 2, 1, -1. And we're going to put our third row up, which is 3, -4, 4, and 6. And then our multiplying factor is going to be our 3 in the numerator divided by -3 in the denominator. And then we multiply the entire thing by 3. So by the -1 rather. Okay, and then when we add these two together, then we get 0, -2, 3, and -7. All right, so this is our equation in our first row and our equation in our third row. And then with this new equation, so 1, 3, we'll call this is equation 5. And so now we can take equation 5, and because it's a combination of equation 1 and equation 3 that we have, we can just replace either this row or this row with our new row. And so we want to leave row 1 the same, as we said earlier. So we're working on our A tilde, that's A tilde prime, so that means this is A tilde double prime. And so we're keeping our first row, so -3, 2, 1, -1. Okay, we didn't do anything at all to the second row. So 0, -2, 5, and -9. And I do want to substitute this into where the third row was. And so we'll use 0, -2, 3, and -7. So now we have a new augmented matrix. And so we've just finished putting the zeros into the right spots for creating zeros by elimination of variables into the first column. So let's move on to the second column. Okay, so we're finished with the first column, and then looking at the second column, let's get our matrix back up there. So this is A tilde double prime is equal to -3, 2, -1, -1, 0, -2, 5, and -9, 0, -2, 3, -7. All right, so now we've got one more 0 to put in here, or one more 0 to convert this so that there's a 0 on the third row, so that we've achieved our upper triangular matrix. And so to do that, we are now going to use our second row as our instrument to eliminate the second column coefficient of the third row. Right, so we're trying to get rid of this -2. And so you do that by writing down the row that you're using. So 0, -2, 5, -9. So this is our, this was equation 4. Okay, it's now in our second row. And then we want to write down our current third row, okay, which is now equation 5, or was equation 5 as we're going through. So 0, -2, 3, -7. And then our multiplier, we have a negative out front, and it's -2 divided by -2. Okay. And so when we add these two together, we get a 0, 0, because we've now eliminated the x2 variables using these rows, and then -2, 2. And so with this new equation that we have, which is a linear combination of equations 4 and 5, right, that gives us permission to substitute equation 6 in for equation 5 or equation 4. And so that means that our new matrix, A triple prime,
Dr. David, someone posted in the chat that 5 might be wrong. Able to check that real quick.
is that right? Okay. Well, let's take a look at it. It is quite possible. What do I get? 0, -2, 3, -7. So it should be a -3.
Well, shouldn't it be 0, -2, 5, and 5?
5 and 5. Yep, looks like it. Yeah, thanks for catching that.
Well, Zach pointed that out.
Yep. Okay, thanks, Zach. Yep, that's right. 0, 0, 2, 5, and 5. Okay, so let's fix this. One second. All right, so I get it fixed.
Looks good.
Okay, great. We'll get these two done as well. All right, appreciate it, guys. And so then, so let's come up with what we got here. So we've got, all right, 0. So it's -1 is what we're doing here. So that eliminates that variable. And so -5. Oh, well, look at that. It gives us 0, doesn't it? Is that right? I have to go back on my algebra and check this, okay? So yeah, there's something screwy here. I'll go back and I'll fix this solution. We shouldn't have the same coefficients here on the left-hand side with two different coefficients on the right-hand side. So that's not possible to have. Let me go ahead and I'm going to write down what I have in my notes, and I'll go back and fix this. But let's say, for sake of argument, that when we do this procedure, we end up with a 0, 0, and a -2 and a 2. All right, and so we're just going to put an asterisk here that's not correct for some reason. Okay, so we'll go back and figure that out, and then we're going to substitute. So that kind of back to where we were on this step is that we've got equation 6 that we can then substitute in for either 5 or 4. Right? And so then putting these together in our final augmented equation, we get -3, 2, -1, 0, -2, 5, and then 0, 0, -2. And then -1, -9, and 2. Right? So that's our new augmented equation. And then this, we've now transformed the entire system into a ux is equal to a b, we'll just call it triple prime, in which we have this now being our upper triangular matrix, where we have -3 to -1, 0, -2, and 5, 0, 0, -2, x1, x2, x3, and that's equal to -1, -9, and 2. All right? So we've just used a forward elimination method to change the AX is equal to B system into a UX is equal to B system. So I hope you can start to see the value of this, okay? Because the ways that we've worked before, we've said that inverting the A matrix is just a bad idea. Okay, there's lots of reasons why it's a bad idea. The second thing we used was Kramer's rule. Okay, and in Kramer's rule, you can expand that to much larger systems. Okay, but we end up with dealing with lots of matrices of minors and getting determinants of minors, and it just becomes actually really computationally expensive. Okay, here, however, by working through each of these multiplications, where we're just multiplying a row through by a single factor, multiplying by a single factor, then it's nice simple multiplication, okay, in substitution, right? And so there's not really complex matrix mathematics or more complex matrix mathematics that are going on. And then we also have by getting an upper triangular matrix and an upper triangular system, we already have an algorithm on which to solve that using the backward substitution. Okay, and so so as we think about what this looks like in a computer program, is that you're creating these multipliers, and so to create this multiplier that we have here, this factor rather, this multiplication factor, I mean, this is negative a tilde, and it's indexing 3, 1, and then we're dividing it by the a tilde of the 1, 1. Okay, and so there's that factor. This factor is equal to it's the negative a tilde of 3, 2. There's a tilde prime rather, and then dividing that by the a tilde prime, and the index is 2, 2. And then the factor for our last one is our a tilde double prime. And make sure I get these right. Oh, I think it was one ahead. Excuse me, guys. That's not 3, 1. That is 1, 1 though. So it's 2, 1, index 2, 1, and then 1, 1. And then this next one is 2, 1, and 1, 1. Okay, so it's our factor for our first row, first column, and for our second row, first column that we're eliminating. And then for our last one, this factor is negative a double prime tilde 3, 2 divided by a prime a double prime tilde 2, 2. Okay, so there's a systematic way that we're working through in this algorithm to be able to get this upper triangular matrix. And so on your cheat sheet that you'll find, this is the forward elimination algorithm, where we're representing a system as an AX is equal to B, and then we change that to an augmented matrix. And then we're going to work by column and by row. So starting with the column, that's your outside loop, and then your inside loop is by row, and you're multiplying row by this particular factor, and then you're adding it to the row that you're interested in. Okay, and working from row 1 to n. Okay, so now, so this is when we combine these two together, where we have forward elimination and then we have backward substitution. This is the putting these two together. So forward elimination plus, or followed by, backward substitution. This is equal to what's called Gauss elimination. So whenever you see this concept of Gauss elimination or Gaussian elimination, it's these two things that go together. And in your book, in I think it's figure 9.3 or 9.4, there's a function that's given to you for what's called naive Gauss elimination. And so naive Gauss elimination is just what we did. We say, I've got a matrix. Okay, I'm not going to mess around with the matrix, the order of the equations at all. And we're going to apply these two algorithms to it and get a solution. Now, that's a naive approach because you're assuming that the ordering of the equations, 1, 2, and then 3, to make an A matrix, right, with equation 1, equation 2, and equation 3 in it, that's appropriate. Okay, we're going to find out tomorrow. There are times where you probably want to order it not 1, 2, and 3, but you may want to go 1, 3, and 2 to be able to accomplish the algorithm. Okay, so there's some decisions like that we'll deal with tomorrow. But for right now, just take a look at that algorithm, rewrite that algorithm, so that it's understandable. You can just take the algorithm and type it into your function and just run it, and it's fine. But I think you will find that as you're working through it, you're going to have to, if you handed that to someone else, that'd be a little hard to understand. So I want you to make that understandable and then use that algorithm on the 2 problems that you're assigned for your practice problems. Okay. And in both practice problems, create the upper triangular matrix by hand. And then in the second practice problem, explain why the naive Gauss elimination algorithm won't work. Okay, so you're going to start it, you're going to run into a problem, and then I want you to be able to explain what's going on here. Okay, and then that's what we'll deal with tomorrow as we're wrapping up this course. Okay, I'll go back and take a look at the, where my mistake was in my algebra. Thanks for catching that, Zach. And then, and I'll post that. I can even just post this solution, a PDF to it, so you can see it and find out where that mistake is and get the right answer. Right. Okay, has anyone done this before? Okay, I know some people have seen it in high school. And okay, and so I want to say that it's another one of these that I think as you work through this, you're going to see that that intuitively makes sense. But for the purpose of this class, I want you to understand it, but I want you to see how it converts over into a numerical algorithm. Okay, and then certainly understand the distinctions between this and inverting A. All right, that's kind of that's the theme of this section. Okay, never take a matrix inverse unless you just absolutely have to. Right? Okay, cool. Any other questions before we wrap this up? All right, I hope you all did well on your WPA. And we'll got one more class tomorrow, and then we'll send you off to the rest of your classes next week. You don't have to deal with this anymore. All right, have a good afternoon, guys.
Thank you.
Thank you.